So let's look at an example where we use this dot product formula. So we're given two vectors in R4, they're called u and v, and we want to compute the dot product of u and v. So we'll just use the formula that we just wrote down at the bottom of the previous page, right? Just compute the product of each respective coordinate and then add up all the products. So for this example, we're going to go the dot product of u and v is just going to be, well, -1 times -3. That's the first product. That's like your kind of like your x1, y1 in the formula of the dot product. Then we're going to take 3 times -4 for our second product. I'll just write 3 times -4 like that. That's kind of like the x2, y2. And then we'll do 5 times 1. And then lastly, 7 times 0. So that's the definition of dot product. So now just work out what all the products are. So this is going to be +3, this will be -12, this will be +5, and this will be 0. So we'll have +3 minus 12 plus 5. Right, I could write the plus 0 too. But anyways, so 3 minus 12 is going to be -9. And if you add 5, you're going to get -4. So that is our dot product, just using the definition. Right? It's fairly straightforward. That formula is really nice. You don't have to worry about computing angles. Well, in this case, you wouldn't be able to. If we didn't have our new definition of dot product, we wouldn't even be able to compute the dot product of these vectors because they're not geometric vectors. They're vectors, they're coordinate vectors in R4. So without our most recent advancement for the definition of dot product, we wouldn't even be able to take the dot product of these two vectors. But we can. So the next note here is just there's a nice relationship between norm and dot product, really. So I'm just going to add it in now. So for any vector x in Rn, you can say the following. The norm of the vector x really is equal to the square root of the dot product of x with itself. Right? There's nothing in the definition that says you can't take the dot product of a vector with itself. And if you do, and then take a square root, you end up getting exactly the norm of the vector. And we can just check that. Now, if I were to work out the square of the norm of some vector x, let's actually let the vector x be written in terms of coordinates. So in the usual way, x1, x2, all the way up to xn. Well, then we can compute the square of its length. And it'll just be, well, the norm of x would be the sum of the squares of each of the individual coordinates, and then you take the square root afterwards. But since it's squared, we can just skip the square root. So you're going to end up getting x1 squared plus x2 squared all the way up to the very last coordinate xn squared. And this next step, you don't even necessarily need to write it down, but I'm just going to write it down anyway just to make it really clear how this actually matches up perfectly with the dot product of x with itself. I'm just going to write x1 squared as x1 times x1, and then I'm going to write x2 squared as x2 times x2, and then up to our very last term, xn times xn. So you can see this is exactly the definition of the dot product in the case where x and y are the same definitions, because instead of a y1 we have an x1, instead of a y2 we have an x2, instead of a yn we have an xn. So really this is literally just the dot product of x with itself. So the square of the norm of x is equal to the dot product of x with itself. So if we just use the fact that this quantity and this quantity are equal and then take the square root of both sides, you end up getting exactly what we said. So the norm of x is equal to the dot product of x with itself underneath a square root. So that's just a nice relationship between norm and dot products. It's not any kind of groundbreaking result. It's just kind of a convenient use of notation, really. Now we'll finish this section off with just some properties of dot products. So this applies to any vectors in Rn. So we've got three vectors u, v, and w in Rn, and we also have a scalar k, which we'll need for one of the properties to state it fully. So the first property just says that the order in which you take a dot product does not matter, which really boils down to the fact that multiplication of real numbers doesn't care about order. So since really multiplication of real numbers is how we build a dot product, it's not a surprising fact that the dot product doesn't care about order. But if you want to say this formally, we can say that the dot product of u and v in this fashion is equal to the dot product of v and u in this fashion. Or in other words, the dot product is a commutative operation. It doesn't care about the order in which you plug in the vectors. Property 2 says that the dot product distributes into vector addition. So what that means formally is that the dot product of u with the sum of v and w, so interpret this carefully, right? We're taking the vectors v and w and adding them together, and the result is going to be a vector whose dot product we take with u. That's what this means. Now it turns out you can distribute this into the brackets and you'll get u dot with v plus u dot with w. That's how I write it, but really what it should say is the dot product of u and v added to the dot product of u and w. So that's our second property. The third property says the following: if I take the scalar k and I multiply it by the dot product of u and v, it turns out there are two alternative ways that I can calculate this. One of the other ways is I can, instead of taking the dot product of u and v first and then multiplying the result by k, I can actually take the k and multiply it onto either of the two vectors as a scalar and then take the dot product. So here's what I mean. I can go k times the vector u, so calculate that scalar product, which the result's going to be a vector, and then I can take its dot product with v. Or I could multiply the scalar onto v instead, and then take its dot product with u. So that's the third way. So all three of those calculations are at least conceptually different, but they will all give you the same result. So you can take them to be the same. So that's convenient as well. The third that was the third property. The fourth property says that the dot product of any vector with itself is always going to be greater than or equal to 0. And really, it's very much, the reason for that is almost identical to the reason for the fact that the norm of a vector is always greater than or equal to 0. And you can see the connection with this rule right here. I'll leave it to you to work out the details if you're interested, but that's our fourth property. And the fifth property just says, and it's related to property 4, this is greater than or equal to 0. It's possible that it could be equal to 0, but the only way that's going to happen is if v itself is equal to the 0 vector. So we can say v dotted with v is equal to 0 if and only if v itself is the 0 vector. So those are the properties that we'll finish this section off with.